All right, eighth graders, welcome to the digital classroom on adding and subtracting rational expressions. Today we're continuing on in chapter 11 and really just kind of honing in a little bit with our skills with fractions, which I know eighth graders like just naturally. So title of the lesson is adding and subtracting rational expressions. In order to do this, we really have to hone in on this word rational and what rational actually means in the math world. Rational really just means it can be written as a fraction. Okay, that's the definition of rational. So rational expressions can be simple, like these couple examples here, and they can be much more complex, like the examples we'll get to. And in order for us to understand the complex, we have to understand the simple. So let's just kind of take a step back and think about fractions. In order to add fractions, one thing that has to be true is the denominators are the same. Remember, denominators are the bottom number. So in order to do something like a half plus 3/2, we would simply add the top numbers. 1 plus 3 is 4. And we would keep the bottom numbers the same as 2, and then reduce any fractions that we see. 4/2 reduces to the number 2. So that's kind of an overview or a quick review on how to add a fraction. If the denominators are not the same, we have to make them the same, right? And this requires us to find the least common denominator, which in these two fractions would be the number 6. In order to do that, with this first fraction, 2/3, I need to multiply the top and the bottom to create something equivalent. This would be equivalent to doing 4/6 plus 1/6, which is 5/6. And then we can circle it and say that this is our answer. Now, if the denominators are not the same and there's no number times 4 that would get you 5, you may need to change both denominators. And again, it comes back to that LCD. Okay, LCD is least common denominator, or the least common multiple of the bottom numbers. Well, if you count by 4s and count by 5s, I believe the first time that they'll match up is the number 20. So all we need to do is to make both of these fractions over 20. Which I think we multiplied this top and bottom by 5 and this top and bottom by 4 to get us, 15/20 and 8/20, which we can then add pretty easily. This is 23/20. And since that fraction doesn't reduce, we've got our answer. So general rules and principles are, okay, same rules and principles will apply to rational expressions. First step is find a common denominator. Second step is add the numerators. And I should actually add this third step, which is simplify. Now, simplify may look different if we're dealing with easy problems like this compared to more complicated problems, but that is the third step, is simplify everything. So we're going to jump into some example problems for today then. Example 1. We've got 4/3y plus 8/3y. Again, if the denominators are the same, we don't have to do anything with these. We don't add these together to make 6y or 6y to the second power. We simply look to the numerators and add them together. 4 plus 8 is 12. And then the bottom would stay the same, 3y. The last thing we do is we look is, can we simplify this? And since we see that 12/3 in this, that would reduce to 4/y. That'd be our complete answer. Second example, or example B, again, denominators are the same. We simply add numerators together. 3x plus x is going to get us 4x. And the bottom number, or the bottom term, just stays the same, x minus 2. Now, we did talk in section 1 about excluded values, or values that would make the expression undefined, or the domain of the expression. In this case, x cannot be equal to 2 because that would create a 0 in the basement. Last one here, expression C. Again, we're looking to the numerators since the denominators are the same. Simply put, 2a plus 3a is 5a, and the bottom would need to stay the same, 3a minus 4. Again, we have to think about those excluded values. 3a minus 4 cannot be equal to the number 0. So we need to solve this for a by kind of working backwards. Add 4, we get 3a is equal to 4. That means a is going to be not equal to 4/3. So we do have to make that disclaimer. A cannot be 4/3. Otherwise, this whole expression would be divided by 0, and we can't have that. All right. So pretty basic to start out with. Again, this is, we're really, really diving deep into fractions. Okay, some of you guys are like, when are we using this? And you know, some answers might say never, but we're diving deep into the discipline of fractions here. All right, we got one more example for you guys today on subtraction. And there's a little catch with this one at the end that you want to watch out for. So this is example 2. Make sure that you copy it down to your notes. Now, when I look at this, I see denominators being the same. Now, the denominator is a pretty complex expression. It's a quadratic, it's a trinomial, it's got 3 terms. So there is a potential that we could, look to factor this, but we'll save that towards the end. Let's just focus in on the numerators to start with. Now, since we are subtracting is the same as addition's opposite. We're going to add the opposite everything here. And then we'll look and we'll say what terms actually do combine. Well, 7x plus a negative 4x is going to get us positive 3x. 5 plus a negative 3 is going to get us a positive 2. And the denominator, since it's, again, similar to the denominator in the second term here, is just going to stay the same. 3x squared minus x minus 2. Okay, so all we've done so far is just added numerators. Now, if you think way back, again, the idea is we want to make sure that the top and the bottom can't be factored. Well, 3x plus 2, there's no number that goes into 3 that also goes into 2 evenly, so that is not factorable. However, the bottom may factor. Let's just write this down over here and see if we can, in fact, factor it. And there's a lot of different techniques we've used. We could slide divide if we wanted to factor it that way. This one, since the numbers are relatively small, you can do the AC method if you remember that method. Numbers are relatively small. Let's just try and guess and check our way there. So we need a binomial times a binomial that would get us this try. Well, let's start with the lead term, 3x squared. That would have to be 3x and x. And then let's move to the last term. It is a minus, which means we got to have one term have a plus after it, one term be a minus after it. And the fact that it's only 2, and 2 really just has the factors of 1 and 2, means we can essentially just kind of play around with where the 1 and the 2 go to make this all work out. So let's just start trying some things. Let's say that we have a plus here and we have a minus here, and I don't know, let's put the 2 in this spot and the 1 in this spot. Remember, we can FOIL this to test whether it is, in fact, the factored version of the expression. So let's try it. 3x times x is 3x to the second power. 3x times a minus 1 is a minus 3x. So that's, again, this part and this part. Positive 2 times x is plus 2x. And positive 2 times negative 1 is minus 2. Combine our middle terms here. This is 3x to the second power. Negative 3 plus 2 is minus 1x or minus x. Ooh, I think I got lucky. I think I chose it right to begin with. Sorry, I'm not showing that correctly. So what we've just done, again, is taken this expression and factored it down to this. Now, the reason why we want to do that is if something cancels, that's good. Just going to get rid of this. 3x plus 2 is one of our binomials. X minus 1 is another. And you guys can see here that we've got like binomials, or like nomials, I should say, on top and bottom. The 3x plus 2 will cancel on top and bottom, leaving us with just the 1 on top and the x minus 1 on bottom. 1 over x minus 1 is our completed answer. And again, x cannot be equal to 1 because that would make the whole thing 0. So when it's all said and done, again, this is a simplified version of what we started with. Look at all the numbers and all the crazy terms that we had here, and it's simplified all the way down to 1 over x minus 1. All right, next video, we'll talk a little bit more about when the denominators are not the same. All right, hope this helped.